Hello class, welcome to Module 4 of Statistics in Introductory Statistics. This week we're going to be looking at continuous random variables. Remember last week we were looking at discrete random variables. So with discrete random variables we have a countable number of values. So say like a fixed or finite, usually finite number of values that the random variable can take, and we have a measurable probability for each one. So this histogram on the left is an example of a binomial distribution. A binomial random variable is discrete. You can see how each value that it can take has a measured probability given by a bar. With a continuous random variable, we can see any value along an interval or along a spectrum. So it's not going to take discrete values. It can take any value along this interval, or it could be, and the interval could be finite or it could be infinite. That's also possible. So this histogram, or I should say this this curve on the right, would be a way of depicting a continuous random variable. So we don't call it a probability mass function. The mass is the kind of the weight of probability on each value. For any particular value, there isn't mass. There is a measure of likelihood given by this curve, and so we call that probability density, not mass. So the random variable's likelihood for any particular value is given by this density function, which we use this f of x to denote. How dense is the probability at any value? And like I said, you don't have any probability for points along this curve. So what's the probability that the random variable takes the value 1.4 precisely? Well, the probability is 0. We don't have any measurable probability for any particular value, only for segments along this interval. You can say, well, how much probability is there that the random variable takes a value between 0 and 1.4? In that interval, you can calculate the mass. You basically just find out what the area is under the curve. That's your probability. So this density curve, this density function, the total area under the curve is going to sum up to 1. That's the characteristic that it has that's going to make it valid for being a probability density function. All right. There's also this cumulative probability function, this cumulative distribution function. We use CDF to abbreviate cumulative distribution function, capital F of x, and it's a left tail probability. So for any value x, it's calculating the probability that for any little value x, it's calculating the probability that the random variable takes a value less than or equal to this. Okay, well, I'm going to give you some examples of continuous distributions in a little bit. If you have taken calculus, you could understand this CDF as the integral of the density function, but don't worry about that because I'm not going to have you doing any calculus in this course. So, all right, let's look at some examples of continuous distributions which are important, continuous random variables. So the first is the uniform distribution, where a random variable can take any value between a lower bound and upper bound. We sometimes parameterize them A and B. There's a lower bound and upper bound. And it's equal likelihood any value along this interval can occur. So this is called the uniform distribution. This is a picture of what the density function looks like. This is a uniform random variable going from 0 to 1. Okay, so it's just a rectangle. If you're interested, you don't have to use this, but if you're interested, the density function is 1 over b minus a, which is to say, in this case, the density is just the height of the rectangle. Okay, well, since the base of the rectangle has a length of 1, the height is going to have a length of 1 also, because the length times the base times the height has to equal 1. The area has to equal 1. Like I said, the area under a density curve always equals 1. Well, that's the formula for the height of the rectangle, 1 divided by b minus a. The mean of a uniform distribution is right in the middle. It's a plus b divided by 2. That's the average of the lower bound and the upper bound. The standard deviation, there's a formula for it, and I don't think you're going to need that, but there's a formula for it. All right, another important continuous distribution is the exponential distribution. And this is often used to model the amount of time until some event occurs. For example, in a business, it could be the amount of time until the phone rings, or the amount of time until a volcano erupts, or the amount of time until, it rains, or something like that. An exponential distribution. As long as certain kind of assumptions are made, like that the events occur there's certain things. I'm not going to get into too much of the details, but so this is what an exponential distribution looks like. There's one parameter. It's lambda. Lambda is a Greek letter. The average rate. How many occurrences per time unit on average we see. So to give you an example, let's say you're dealing with hours, and let's say you get 5 phone calls per hour on average. Well, you'd plug the number 5 in as your parameter, and then you could then use this exponential distribution to calculate, okay, what's the probability that it takes 3 minutes until my next phone call, or 7 minutes, or 45 minutes, or whatever. The density function is this f of x. It's lambda times e to the negative lambda x. Now, I'm not going to expect you to use the density function. You can look these up also. But one thing that's good to know, the mean and the standard deviation are both equal to 1 over lambda. So if you, on average, get 5 phone calls per hour, the mean amount of time between until the next phone call is 1 over 5, 1/5 of an hour, 12 minutes. Okay, and here I'm just showing you a handful of other continuous distributions. The beta distribution is useful for modeling an unknown probability. The Gaussian distribution we'll talk about more in depth next week. It's also called the normal distribution. There's a gamma distribution, which is related to the exponential, and it's a way of kind of measuring how many occurrences. Let's not get into that right now. Okay, the F distribution. Okay, so all of these are just different continuous distributions. And we will only use a couple of them in this course. I'm going to post a second video which shows how to use stat powers to calculate continuous distribution probabilities and percentiles, but that's the end of this lecture. All right, talk to you later. Bye.